For number 21, we're asked to find a power series representation for the natural log of 1 plus x all over 1 minus x. Start by doing a division property of logs. You would find that you have the natural log of 1 plus x minus the natural log of 1 minus x. Now, really we need to get to some power series that we recognize, specifically working as much as we can with 1 over 1 plus x or 1 over 1 minus x. As I said earlier, over and over again, we want to work with one of those two functions in their power series representations. I hope you can quickly recognize that when we take the antiderivative of 1 over 1 plus x, we will get the natural log of 1 plus x, assuming, of course, that x is going to be positive in this regard. Otherwise, of course, we'd need absolute value. But as we also move on, we can very well see that there's going to be an integral of 1 over 1 minus x dx. But please realize that if I took an antiderivative of this, 1 over 1 minus x, we'd have to reverse the chain rule. And we'd wind up actually having a plus right here. Now you can always double check if you're right by taking derivatives of these natural logs right here to more or less check that we are correct in finding these integrals, which are the antiderivatives, of course. But as we proceed, I hope you remember that this 1 over 1 plus x, well, this first integral, this is that geometric series where we'd have a common ratio of negative x. So we'd have 1 minus x plus x squared minus x cubed plus x to the fourth. Could even go a little bit further if you'd like. This would be minus x to the fifth, etc. I'm not even going to include an nth term at present. But this 1 over 1 minus x, well, that's where we even began our lesson on this section. We recognize this as a geometric series, and this might be actually a little bit simpler as we're working this all out. So, we'd continue on, say here's your dx. Well, these antiderivatives, of course, are going to involve for us to actually take antiderivatives. Remember, we'd need a constant if we don't have boundaries here. That's very important. Antiderivative of 1 would be an x. Then this would be minus x squared over 2 plus x cubed all over 3 minus x to the fourth all over 4. And then we could say plus x to the fifth all over 5. This thing right here, we bump up x to the sixth, divide by 6, and we're going to continue on with this pattern going on forever. But then we're going to say over here, this will be an x, and then we'd say plus x squared all over 2, plus x cubed all over 3, plus x to the fourth all over 4, plus x to the fifth all over 5, plus x to the sixth all over 6. You get the idea. Don't forget, we'll also have a little constant added at the end. But first things first, it doesn't take students long to see that the x squared terms are going to cancel, the x to the fourth terms are going to cancel, the x to the sixth terms are going to cancel. In fact, what you will quickly notice is all these even powers of x are in fact going to cancel out. What are we going to be left with? Well, we'd have this, 2x. We'd have an x cubed over 3 and an x cubed over 3. That would be 2x cubed all over 3. We'd have 2x to the fifth all over 5, etc. And this will go on forever and ever. Don't forget, we'll also have a little constant that we're going to add at the very end. You don't want to forget about that. But you might wonder, what would this series really look like? What's this really saying? Well, if you look very closely, you're going to notice that every single term has a 2 in it. So I'm going to put sigma right over here, and I'll say I'll definitely have a 2. You're going to notice every power of x is odd. I can very quickly note that if 2n is an even term, of course, because it's a multiple of 2, 2n plus 1 would be an odd term. You're going to notice that the same odd number is going to go down below. And if you look at your counter, you might guess that we could begin at n equals 0. It's very important for us to check and see if this really is generating what we'd like for it to generate. Go ahead, let n equal 0, let n equal 1, let n equal 2. You'll quickly see that you generate this. A lot of times we'll put the C plus in front just so that no one would get confused to think that you add a constant to every single term in this expansion, like each individual, like the first term and so on, would each have a plus whatever that constant is in it. Really, it's just one singular constant. But this is a power series representation for what we're looking to find.